Hello everyone. Today we're going to be talking about quotient fields. So quotient fields are essentially uh, analogous to constructing rational numbers out of integers, right? So taking some ring in specific integral domain and allowing multiplicative inverses. Okay, so let's remind ourselves of what an integral domain is. So R is going to be an integral domain which is commutative and it has no zero divisors. So, and zero divisors are non-zero elements which multiply to zero. So an example of zero divisors is typically given in, say, like a mod, like Z mod 4Z type of ring. So you could have 2 and 2. They multiply, well, 2 times 2 is 4, so in Z mod 4Z that would be 0. So Z mod 4Z is not an integral domain. But the integers are an integral domain because if you multiply two non-zero integers, you get a non-zero integer. So that's what we're going to be dealing with. And what we're going to do to construct the essentially the fractions on R is we're going to let A, B, and C, D be pairs of elements in R with the second pair being non-zero. Um, then we say that these pairs are equivalent, so we're going to define an equivalence relation on essentially R times R minus 0 uh, if AD equals BC. Okay. And so to show that this is actually an equivalence relation, we would have to show three things. One is that if something is equivalent to itself, so this is you know uh, AB equals AB, which is obviously true. Okay. And then two is excuse sorry, I had to sneeze. Um, is that if AB is equivalent to CD, then we would have to show that um, CD is equivalent to AB. But this is true because the multiplication is commutative. It's like this is saying CB equals DA, and these are obviously just the same statement because our ring is commutative. Okay. And then the only like non-trivial one is transitivity. So for transitivity, you would have AD equals BC and CF equals DE. And you want to show that AF equals BE. Okay, so here I'm dealing with three fractions. You can imagine how they're labeled A over B, well, AB, CD, and EF. Um, and so what you do is that you take these two, and you multiply this one by F. So you have ADF equals BCF. And then BCF is equal to B times DE. And then we take this equality and we subtract on both sides BDE, and we can factor out a D. So we get D is AF minus BE, and that's equals 0. And since R is integral and D is non-zero, we know D is non-zero by assumption here, right? D is non-zero, and since this is an integral domain, this implies AF minus BE is 0. Okay, so this shows that squiggle is actually an equivalence relation, And what equivalence relations allow us to do is essentially take quotients or look at equivalence classes which are well defined. So we get well defined equivalence. I cannot spell equivalence classes, and we denote those by the fraction. So A over B stands for an equivalence class of pairs AB, and so we could choose two different pairs so long as they're equivalent, right? So a fraction has two different pairs. And so A over B is the equivalence class for AB. Of course, we could pick any other representative, and it would be the same equivalence class. Okay. Okay. The next thing to do is to define algebraic operations on our fractions. So we define a over b plus c over d, and of course we're just going to define this in the natural way. Okay, and then same thing for multiplication. We define a over b times c over d as ac over bd. And so what you have to check here is that since we're defining things in terms of equivalence classes, is that you have to check that if I were to pick a different representative here, that you would get the same equivalence class on the right. Okay, and I'm not going to go through these details because they're rather tedious, but if you want to, you should show that. But the important part is that these are well-defined operations, and you can check that they're well-defined. It's just a bunch of, you'd have to deal with a lot of letters, and I'm not going to go through that. And so this actually turns, well, we need two more things. So from these definitions, so from these definitions, 0 over 1 is a plus identity, and 1 over 1 is a multiplicative identity, right? So if I plus 0 over 1, I get a times 1 plus 0, so that's just a here, and then I get b times 1, which is just b, so I get a over b. And then here, if I multiply by 1 over 1, I get a times 1 is a, b times 1 is b, so this is a over b. So thus, the set of these equivalence classes is a commutative ring. Okay. And we're going to call it K. Now this is actually more than a commutative ring, and we're going to show it's a field. So if a over b is equal to 0, well, the 0 element is 0 over 1, then this means that essentially we can think of this as saying the equivalence class AB is equivalent to the, sorry, not the equivalence class, but the pair AB is equivalent to the pair 0, 1. And so this means that A times 1, which is A, is equal to B times 0, which is 0, so A equals 0. Thus, if A over B is non-zero, then A is non-zero. So again, I'm gonna make it explicit that here when I'm saying that a fraction is non-zero, it's not equal to 0 over 1, but later on I'll be less technical with that. So if A is non-zero, then that allows us to think about the B comma A has a well-defined class B over A, right? Because remember, to define this equivalence class, we needed that the second term was non-zero. The first term can be 0, but here we're saying that we know that if the fraction is not 0, then the first term is not 0, so we can actually flip the terms, and we get a fraction b over a. And then you can check that a over b times b over a is ab over ab, which is 1 over 1, because ab times 1 equals ab times 1, right? Thus, every non-zero element in K has a multiplicative inverse. It's a mult inverse. So K is a field. And this is what we call the quotient field of R. So again, if you were to carry out this construction with R equal to the integer z, then you would get the field of rational numbers Q. Okay. So this is a construction for turning a integral domain into a field. Well, not turning it into, but creating a field out of it. There's a similar construction in commutative algebra called localization, which is outside of the scope of what I plan to cover, but is kind of similar. Okay. So not only does this quotient field sort of, not only are we constructing a field out of our ring, or from our ring is actually naturally embedded into the field. So what I mean by that is there is a map, I'll just call it F from R to K, which sends the element A to the fraction A over 1. And you can check that this is an injective ring homomorphism. And typically injective, well, you also see this not even in algebraic terms, but sometimes with manifolds. I talked about this, and I believe I talked about this in my manifold series. But typically injective maps are called embeddings. And we'll see this a lot more in field theory and Galois theory later on. But these types of maps are called embeddings. Why are they called embeddings? Well, we know that if a homomorphism is injective, then the kernel is 0. So essentially you get the image f of R is a subring of K, which is isomorphic to R. So essentially the idea is that we can think of R being a subring of K. It's not technically correct, but there are essentially elements in K which mimic R, is a way you can think of it. So in rational numbers, right, we kind of think of integers being inside the rational numbers, although in this construction, right, sort of from a really from a really precise point of view, you would say like, no, the integers are isomorphic to a subring of the integers. Of the rational numbers, right? But for all intents and purposes, like it's fine to think of the integers as actually being a subring of the rationals. Okay. Now let's look at what happens if you're given a field F, and you have some subring inside of F. So note that if you take a subring of a field, then this ring is automatically going to be an integral domain. Why? Well, in a field, you necessarily have commutative multiplication. So the multiplication that R inherits is going to be commutative. And then, well, we know that any element in R, it has a any non-zero element has a multiplicative inverse, not necessarily in R, but in F. And so this means that R can't have zero divisors because F doesn't have zero divisors. So R is necessarily integral. So we can form the quotient ring, and it turns out that K, the quotient ring, is isomorphic to the set of A times B inverse, where A and B are in R, and B is not equal to 0. So this kind of looks like how we defined, this kind of looks like how we defined K, but in a sense it's different because we didn't know to start with that if I take an element in my ring, we don't know in general the meaning of B inverse. But since B is a non-zero element in F, right, so B being an R means B is an F. So B inverse is an element of F, not necessarily in R, right? So we're kind of presupposing that we have a ring that's sitting inside of a field, so we can take inverses, but it just might not be an R. So this is like a nice way to, if we know that our ring is in a field, we know what the quotient field looks like in a very nice way, right? We don't have to deal with equivalence relations, and it is what I'm trying to get across. And we can actually just deal with elements of the field that were given already. Okay. The last thing is going to, again, be something that sort of mimics stuff that we'll see in Galois theory. So let F from R to F be an embedding of an integral domain R into a field F. Okay. And so again, whenever we deal with embeddings, we can think of it as R being a subring of F, although this is slightly more general. Okay. Then there is a unique extension F star from K to F, which is also an embedding. So what do I mean by an extension? So here K is the quotient field of R. And what I mean by an extension is I mean that F star, if you take it on elements of R, is going to line up with F. So kind of, well, so what I mean is that if A is an R, then F star of A over 1, which is what we think of an element of R being inside of K, this should equal F of A. So that's what I mean by an extension. Okay, so let's look at proving this. The proof is kind of simple. So So we actually define f star of A over B to equal f of A over f of B. Okay, so what's the issue here? Well, the issue is that since we're defining a map on K, which is a set, well, a field, but a set of equivalence classes, we're defining things in terms of particular representatives A and B for this equivalence class. So we need to check if A over B equals C over D implies f of A over f of B equals f of C over f of D. And this is actually the case because if A over B equals C over D, AD equals BC, and so we can apply f on both sides. And then since f is a homomorphism, we can break up the multiplication. And this shows that the fractions are indeed equal. So that this map is well defined. And then we know, since f is a ring homomorphism, we know f of 1 equals 1. So f star of A over 1 is f of A over 1. And I guess. Oh, I should I should technically be saying that this is f of B inverse. Since we're dealing with an arbitrary field here. So there's some more details to iron out in that case. So we're assuming B is non-zero. So f of B is also non-zero because the kernel of f is 0. Why is the kernel 0? Because we're assuming f is an embedding, which means the kernel is 0. It's injective. So that if I plug in a non-zero element, I have to get a non-zero output. Therefore, f of B inverse makes sense, and so that this is how I should have defined it. Okay, and then clearly, since f of 1 equals 1, f star of A over 1 is f of A times 1 inverse, which is just f of A. So this shows the existence. So this is existence. So I've claimed that this exists, and I claim two things. I claim that there is an extension, and then I claim that the extension is unique. So I've showed the existence of such an extension, and I guess I should also show that this is an embedding. So f star of A over B equals 0. So this is f of A, f of B inverse. So if this equals 0, then, well, f of B inverse can't be 0. So f of A equals 0. And then since f is injective, so A is 0, since the kernel of f is 0. And then A equals 0 means that A over B is 0. 0 over 1. So the kernel of f star is also 0. And then if you want it to be super technical, you should check that this is a homomorphism, but that's pretty simple. Okay. Okay. Now we have to show uniqueness. So uniqueness Well, we know that if I take f star of A over B, then this is the same thing as f star of A over 1 times 1 over B. Okay. And so 1 over B is... So since f star is a homomorphism, I can break this up. And then 1 over B is the inverse of B over 1. And since f star is a homomorphism again, I can pull inverses out. So this becomes f star of A over 1 times f star of B over 1 inverse. And then since f star is an extension, I know that f star of A over 1 is f of A, and then I know f star of B over 1 is f of B, and so I showed that if I know nothing except that f star is an extension, is a homomorphism K to F that extends F, then I've shown that it must satisfy the way I defined it here. So I showed that this exists and it satisfies these conditions, and then this shows that this is the only map that satisfies the conditions. So this is a kind of standard argument for uniqueness theorems, right? You have to show it exists, and then you have to show that that those properties imply that that example that you gave is the only thing that satisfies those conditions. Okay, so this is an example. If this is your first time seeing a uniqueness thing, then you might want to sort of study this a little bit. Okay, so hopefully this video helped, and I'll see you in the next one.